So the outline of this lecture is going to be, first I'm going to provide a brief review of what we covered last lecture in terms of determining your position relative to a series or constellation of satellites. From there, we're going to go into a little bit more detail about the signal components, how the signals are structured, modulated, what the frequencies are at a very basic level. And then in addition, how do you determine your location using those signals? And that's going to involve ranging codes and a navigation message. Following that, we're going to cover a little bit of detail about GPS receivers and different quality receivers and what that means for your position, as well as how the system is being modernized and continuously updated. So to review, your distance from any given satellite is based on your time of arrival, or TOA. So you calculate the time difference it takes for that signal to propagate from the satellite to the receiver, and you multiply that by the speed of the signal. So in this case, the speed of light. So by doing that, you get your distance from any one satellite. By using a series of satellites, you can determine your location. Now, in the instance here on the left, we use 3 satellites, and in a 2D world, that's fine. You can determine your location. However, to determine your true 3D location in a 3-dimensional world, you actually need 4 satellites. So here's a graphical representation of your distance from one satellite. You can be anywhere on the sphere here. If you have 2 satellites, now you're limited to essentially a ring where you could potentially be. 3 satellites, you're actually possibly at 2 points. So one of those is likely going to be on the Earth, and the other one is going to be either above or below the Earth. In order to determine which one you're at more precisely, you need a 4th satellite. That 4th satellite essentially adjusts for the receiver clock error, and by having more satellites, you're able to more accurately account for that receiver clock error and get a greater accuracy of your position. So also a reminder that the 3 major segments of GPS are the control, space, and user or receiver segments. Also, the constellation, so the space segment, was updated in 2011 to be a expandable 24 configuration. And what this actually means is that there's 27 or more satellites operational at any given time. So there's a traditional block of satellites, that's blocks 2, 2A, and 2R, and some of those are still in use today. But then there's also the modernized satellites, which is the blocks 2RM and 2F and GPS 3, which provide greater level of precision. So the purpose of this lecture is primarily going to be providing you with a background about how the GPS signals operate, how they're modulated, and how you determine your position using those signals. So the GPS operates on a radio wave frequencies, and there's a sine wave and a digital ranging code. So based on those two, the sine wave and the digital ranging code, you're able to determine your distance or range from the receiver to the satellite. Now, in addition to that, you also need the navigation message. So the navigation message is actually the coordinates of the satellites and other information. So we'll cover this a little bit later in lecture, but this is information such as the ephemeris and the almanac of the satellites. So GPS is modulated on a couple different frequencies. So there's a L1 carrier, there's a L2 carrier, and by using the combination of the L1 and L2 carrier, you can correct for ionospheric delay. Now, I will cover in a few slides what the ionosphere is and why it delays the signal, and we'll go into that more later in the lectures as well. But right now, all you need to know is that the L1 and L2 carriers, by using the combination, allows you to correct for that ionospheric delay. There's also an L5 carrier that's a little bit newer. It's only used in some certain instances, but once again, that can allow you to more accurately determine your position. You won't be asked to know what frequencies they operate at, just know the names of the carriers. Now, there are a couple different types of digital ranging codes. So traditional GPS satellites use a CA code, which is a coarse acquisition code, and you need to know that. That's modulated onto the L1 carrier only, and that's a very coarse positioning. There's also the P code, which is a precision code. You need to know that as well. The difference between the two is that the P code is modulated on both the L1 and L2 carriers. So remember in the previous slide I said that you could account for ionospheric delay if you were using L1 and L2 carriers. If you're just using the L1 carrier, you can't account for that ionospheric delay. So it's important that you be able to use your CA and your P codes. The modernized GPS satellites have additional frequencies, so they also operate on the L2CM and L2CL. That's L2 civilian moderate code or L2 civilian long code. There's also an L5, as I mentioned, that's a high performance application code. And then more recent satellites have an L1C, which is really designed to facilitate interoperability between all the different international systems. So the way the signal is structured is it's actually structured as a PRN, or a pseudo-random noise code. Now, we covered this briefly in previous lectures, but we're going to go into it a little bit more detail here. So a PRN is actually a stream of binary digits or bits or chips. So it's either 1 or 0. And by modulating that code either on or off, ones or zeros, you can actually create a unique PRN code. So what this is called is biphase modulation. In other words, that carrier phase is shifted 180 degrees when the bit changes. So when you go from 0 to 1 or 1 to 0, you're shifting that phase. So our CA code, as mentioned earlier, is a course acquisition code. It's 1023 bits long PRN code, and it's transmitted at 1.023 megabits per second. You don't need to know that necessarily. The biggest thing is that one bit equals or equates to about 300 meters of accuracy. So this is a very coarse level of precision or accuracy. So each satellite has its own code that's highly orthogonal or different from all other satellites. So by doing so, you can determine which satellite you're receiving the signal from based on the CA code. So the CA code enables your receivers to identify which satellite, and by doing so, you can determine where you are, because you need to know what satellite you're receiving it from in order to determine your position. CA code ranging is less precise than P code ranging, and this is because the CA code is less complex and it's available to all users. Also remember, I said this is modulated only on the L1 frequency, as opposed to the P code, which is modulated on the L1 and L2 frequency. So when we go to P code, now we're talking about a much longer string, a much longer code, and it repeats itself every 266 days. What this means is that by having that more complex code, you're able to more precisely determine your distance or your location from that satellite. So by the combination of CA and P codes, each satellite has a unique combination, so you can determine which one you are receiving a signal from. Now, we also introduced in one of the previous lectures what anti-spoofing is and selective availability. So we're going to cover anti-spoofing a little bit here. They're both designed to do similar things, but they both manipulate essentially that PRN code. So in the case of anti-spoofing, it's designed primarily for military purposes, basically to encrypt the signal. So it's an intentional encryption of the signal by adding an unknown W code and getting a Y code. So what that does is that manipulates that PRN code into providing the user with a false sense of position. Now, it's also important to note that anti-spoofing is no longer in effect. It has been done away with. Now that we have the CA code and the P code, we need some additional bits of information. So additional bits of information would be where the satellites are currently located, where they're expected to be located. How do we correct for that ionospheric delay? So ionospheric correction model parameters. This is all contained within the navigation message. So the navigation message is a binary message which is added to both the P and the CA codes. So once again, it's modulated on the L1 and L2 carrier frequencies. So the complete navigation message is 37,500 bits, and it's transmitted in approximately 12.5 minutes, 12 and a half minutes. So some of the information that's contained within the navigation message is the broadcast ephemeris. So what that is the coordinates of the GPS satellites as a function of time. The satellite clock correction model parameters. So there's, as we'll see later on, there's actually slowing down and speeding up of the clocks based on where they are in the satellite orbit. It also contains information about the health status of each satellite, as well as the almanac or predicted locations of the satellites in the future. There's also ionospheric correction model parameters, as I said earlier. The navigation message was recently updated from nav to CNAV. Now, the biggest reason for this shift, for this update, was to increase GPS to GNSS interoperability. By that, what I mean is increase the interoperability or the ability of a user to use signals from the Navstar system as well as Galileo, as well as GLONASS, as well as Beidou 2. And we'll cover that a little bit more later. But by updating to that CNAV navigation message, you have that improved interoperability. So I mentioned earlier that there's ionospheric delay model parameters that need to be accounted for that are contained within the navigation message. Well, what is the ionosphere? What do I mean by those ionospheric correction parameters? So the ionosphere is an ionized upper atmosphere layer, and it's ionized by solar radiation. So solar radiation comes into this layer, impacts gas particles, and actually excites the electron clouds. And so what this does is it's ionized particles within this layer that actually influence the propagation of radio waves or all electric activity. So it absorbs cosmic rays, gamma rays, X-rays, and some UV rays, so it's beneficial, but it's also problematic when we're trying to transmit a signal through this layer. So now that we've gone over a little bit about how the signals are structured, I'm going to go into just briefly what some of the commercial GPS systems are and how the system is being modernized. So there's a variety of different commercial GPS receivers. Multi-channel receivers can handle anywhere from 9 to 12 independent channels. So what that means is that each channel continuously tracks a particular satellite. So you can receive and process signals from up to 9 to 12 satellites. Now, the upper left here is the receiver unit that you'll use for the class. There's also a variety of different other receivers. So on the left, kind of center, you see a Garmin Forerunner. Those have GPS built in them. At the bottom, you see a dog collar GPS. You can still get that. Now, everything on the left is a little bit coarser in its positioning. If you really want to determine your position very precisely and accurately, you're going to want equipment similar to the one on the right here. Now, what that is geodetic quality equipment, and it actually it actually uses an external base station to account for delay of the signals. And we'll cover that later in the class. Once again, with commercial GPS receivers, there's single frequency code receivers. Now, these only receive your CA codes. Remember, that equates to about 300 meters of position accuracy. So, not the most accurate in the world because you're limited to only the CA code. There's also single frequency carrier smooth code receivers. Now, what those are is they still operate only with a CA code, but that carrier frequency is processed internally by the software, which gets you that higher resolution. So they're a little bit improved accuracy with those receivers. The next step up is to have a single frequency code and carrier receivers. Now, what this is it has a CA code modulated on an L1 frequency, and it also has that navigation message. So that navigation message has, remember, ionospheric model parameters and other information that you can further improve the accuracy. Improving on that is a dual frequency code receiver. Now, a lot of receivers tend to be more dual frequency nowadays, where you have a CA code and a P code. It used to be you would potentially have a Y code. Remember, that was done away with though. So right now you only have the CA and the P code. Now, because you have the P code as well, remember that's modulated on the L1 and 2 frequencies. So dual frequency code receivers actually are able to receive and process signals from the L1 and L2 frequencies. You also have, once again, the navigation message information. You have that ancillary information that you can use to more accurately determine your location. So for further information about GPS modernization of the system, of the constellation, I'm going to refer you to an external GPS modernization slide. Now, because the GPS modernization schedule and status changes frequently, we're not going to include it in here, but refer to that external slide. Additionally, if you wanted to get more up-to-date information, you can just go to gps.gov, and under there's a GPS modernization page, and that'll tell you a little bit more information about the modernization of the system and how we're working to keep it up to date. So if you hadn't figured out up to this point, satellite systems, GPS, uses time as a basis for positioning. So time plays a very critical role in determining your position with GPS. So GPS signal, remember, is controlled by the highly accurate atomic satellite clocks on board the different satellites. And the clocks on board those satellites have changed through the different generations to provide you a more and more precise measure of calculating time. So the distance or range from any given satellite is based on the receiver and satellite clocks. And so in order to do this, you have a coordinated universal time, in this case GMT. So that's the atomic time scale based on the International Atomic Time. GPS time is monitored by the monitor stations and onboard GPS satellite clocks. So the latest difference between the GPS and the UTC timescales is given by the GPS navigation message. So if you want more information about the different time systems, you can go to leapsecond.com/java/gpsclock.htm, and that'll bring you up a page which contains something like this. The time is going to be continuously updated, so you'll see it counting up every second. But you can also see that there's a mismatch, that the local time is not the same as the UTC time, which is not the same as the GPS time or the LORAN or the TAI time. So how do we measure our distance from a given satellite? We hinted at this in a previous lecture. We're going to go into it a little bit more now. So PRN measurements are a measure of distance between the GPS receiver and GPS satellite antenna. So remember that satellite transmits a PRN code that matches one stored by the receiver. Based on the alignment of that code, you can calculate the time difference and ultimately the distance from that satellite. But that distance is contaminated by some synchronization error. Now that synchronization error is caused by many different reasons, but it occurs between the satellite and the receiver clocks, and it also has other errors and biases as well. So the modern receivers typically store a complete set of pre-computed CA code chips in memory. Remember, the CA code allows you to determine which satellite you're receiving the signal from, so it's important that you have a pre-computed consistent set of CA codes. So the way this works is the receiver slides the replica of code in time until it finds a correlation with the satellite signal code. So in the graphic example here, say we have a receiver generated signal and that same signal is transmitted by the GPS satellite. So at the bottom, your receiver generates it at such a time and then it receives it at another time, the middle diagram here. And so based on that time difference, it's able to calculate your distance from that satellite. However, we also know that there's error in the receiver generated signal as well. So by accounting for that, we're able to determine your true distance from that satellite. So if a receiver applies a different PRN code to a satellite signal, you get no correlation. So that's the example on top here. Those signals don't match up. Those bits of ones or zeros don't match up at all. And so you're not able to use that satellite signal to determine your location. However, when the receiver uses the same code as the satellite is transmitting, you can start to get the code to align. Now, this is where you may see the bar, the status bar on that satellite jump up a little bit or halfway up, but it won't go all the way up. What that's saying is basically you're receiving and identifying that signal and you're able to receive it, but you can't match it up perfectly. So you can't identify your location relative to that satellite until you have a better lock. Now, the ideal case is when the receiver and satellite codes align perfectly. This is when you get the full power from that satellite and when you can determine your location from that point. So this is usually done by a late version of the code being compared with an early version of the code to ensure that the correlation peak or that match is tracked perfectly. Hopefully you have a little bit better understanding of how the GPS signals operate. Remember, they're modulated on a couple of different frequencies. So there's the L1 and L2 carriers. In addition, there's subsets of that. So there's the L1 CL, L1 CM carriers. There's a L5 carrier. So you need to know that. You also need to know that the PRN code is modulated either in the form of a CA code or a P code, and what that means for your level of positioning accuracy. You should also know what anti-spoofing is, how it works. Also know it's not in effect today. The next lecture will go over GPS satellites more specifically and their orbits. So you'll get a little bit more information about how the constellation works and some of the ins and outs of it.